Welcome to this video with an example of analyzing determinate structures. This is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. One objective in this example is to get into the habit of drawing bending moment diagrams without setting up equations. Rather, we wish to simply use equilibrium. Remember, for statically determinate structures, the consideration of equilibrium is sufficient for determining all the internal forces in the structure caused by external loads. The basic idea for establishing the bending moment diagram for beams and frames is to calculate the moment at selected locations once we have found the reaction forces at the supports. The fundamental idea is that moment is force multiplied by arm. This example is sufficiently simple for us to skip the calculation of reaction forces. Instead, we determine the bending moment at the two ends of this beam. On the right-hand side, the moment is 0 because this is a free end. On the left-hand side, the bending moment is F times L, which is simply force times arm. Once we have the bending moment value at the two ends of a member, as we often obtain in more advanced methods for statically indeterminate structures, we draw the bending moment diagram between those two values. This beam does not have any loads acting along the beam between the two endpoints. For that reason, the bending moment diagram is a straight line between the known values. Notice that the convention in terje's toolbox is to draw the bending moment diagram on the tension side. It is important that you are able to see that the beam experiences tension at the top on the left-hand side. Perhaps you find it obvious in this case, because the load, F, is acting downwards, bending the beam so that tension will occur at the top. It is good if you already have that understanding. If you do not, then it helps to hold one end of a plastic ruler in your hand and apply the point load at the other end. You may then find it easier to understand which side is in tension. In these examples, we always draw the bending moment diagram on the tension side. Because some textbooks draw the bending moment diagram on the compression side, it is often smart to state your convention, in order to avoid misunderstandings. Next, we consider the case of uniformly distributed loading, Q, on the beam. Notice that we again start by calculating the bending moment value at selected locations. In this case, the selection is obvious. We calculate the bending moment on the left-hand side as resultant force multiplied by arm. The resultant force is Q times L. The distance from the left-hand side to that resultant is L over 2. The resulting moment is then QL squared over 2 with tension at the top. Let us now make a couple of points related to the shape of the bending moment diagram. Although we would normally not do this, we start by calculating the bending moment value at the middle of the beam. Do you see how the resultant of this load is Q times L over 2? And that the arm of that resultant relative to the midpoint of the beam is 1/4 of the length of the beam? The result is that the moment at the middle of the beam is QL squared over 8, with tension at the top. This leads to the bending moment diagram that is highlighted with yellow down below. Now that we have the value of the bending moment diagram at the middle of the beam, we are able to find the depth of the parabola that the bending moment diagram forms between the endpoint. Remember from an earlier video that uniformly distributed load along a member gives a parabolic shape of the bending moment diagram. Because the value of the bending moment diagram at the left-hand side is QL squared over 2, the value of this green straight line at the middle of the beam is QL squared over 4. We conclude that the depth of the parabola is QL squared over 8. This is an important conclusion from the calculations at the midpoint, which we would normally not do. The observation we made has two significant ramifications. First, we can split this bending moment diagram into a triangle, which comes from simply drawing a straight line between the two known bending moment values, and a parabola with tension at the bottom, which accounts for the effect of the distributed load between those 2 points. Second, we have made an observation that is valid for all continuous beams. The variation of the bending moment diagram between 2 points is always a parabola with depth QL squared over 8, where Q is uniformly distributed load and L is the distance between the 2 points. It does not matter where we select the 2 points, but we usually select the two endpoints of a member. What we have now seen is one reason why structural engineers sometimes use the value QL²/8 without more detailed analysis, because the bending moment value in a continuous beam cannot exceed QL²/8. The single exception is cantilevered beams, which we addressed above, which has a bending moment value at the base equal to QL²/2. Before we address the step from the bending moment diagram to the shear force diagram, the point is here made that we use the same approach even if the load is not uniformly distributed. Here is a cantilever with a triangular distribution of the load intensity. When the triangle is oriented like this, the bending moment at the base of the cantilever is QL²/6. Now, let us determine the shear force diagram from the bending moment diagram. It was mentioned in another video in this course that some instructors prefer to start with the shear force diagram and integrate it in order to obtain the bending moment diagram. That is a valid approach, but it can be cumbersome for some frames, and many methods in advanced structural analysis give the end moments of the members as the primary result. Examples include the stiffness method and the moment distribution method. So, let us practice how to go from the bending moment diagram to the shear force diagram. Here is the bending moment diagram for the cantilever with a point load, F, at the tip. We know from beam theory that the shear force is the derivative of the bending moment. Mathematically, we say that the shear force, V, is dm/dx. Because the bending moment diagram is a straight line in this case, the value of that derivative is calculated simply as the change in moment from one end to the other, divided by the length of the member. That means we divide F times L by L. The result is F, and that value makes sense, because F is the point force at the tip of the cantilever. However, we need to pay attention to the sign of that shear force. Because of the way the load, F, acts, you may intuitively see that the shear force tries to rotate each segment of the beam clockwise. In the conventions adopted at terje's Toolbox, clockwise shear force is considered positive. When we also have adopted the convention of drawing the bending moment diagram on the tension side, the following consideration is necessary, in general, in order to determine the sign of the shear force. When you follow the axis of the beam or frame member, going from left to right, just like the x-axis of any mathematical function runs from left to right, then a downhill slope of the bending moment diagram means positive shear. In short, the value of the shear force is the derivative of the bending moment diagram, and the sign of the shear force is positive if it is an easy downhill walk along the bending moment diagram from left to right. One way to remember this is that an uphill walk is tougher and therefore negative. An identical consideration is made here on the last page for the case of a uniformly distributed load. The bending moment diagram is a parabola, and the shear force diagram is therefore a straight line. It is straightforward to see in this case that the shear force value on the left-hand side is Q times L, because that is the total load on the beam. In practical applications, it is not necessary to carry out that kind of consideration, or explicitly differentiate a mathematical function. That is because we noticed earlier in this video that bending moment diagrams can be split into basic shapes, such as triangles and QL²/8 parabolas. To find the shear force diagram associated with such basic bending moment diagrams is straightforward. Here you may refer to the video on analysis of determinate structures, where a few formulas to remember were given. Such formulas for simply supported and cantilevered beams, which are easy to derive and remember, are all you need in order to go from the bending moment diagram to the shear force diagram. Examples and other videos posted near this one will show how you go from the shear force diagram to the axial force diagram. That was not relevant in this video because the beams considered here did not experience axial force. Thanks for watching this video. Please visit terje's Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.